Hello, everyone. Welcome back to another video on organic chemistry. Hey, so right now we're in Key Concept Unit 3, Part 3, 3 and 3. And we're about to unfold a huge amount of information. So get ready. This section is a little different than what we've seen before. What we've seen before is like, hey, here's a reagent. And look, it reacts with a functional group that changes into a new functional group. Okay, this section is different because what we're going to see is a pattern. We're not going to discuss one specific reagent. We're going to discuss a type of pattern, a reaction mechanism that's common to a whole bunch of different reagents. Okay, so this section, the way to get through it is to identify the mechanism and know the pattern of that mechanism. So that when you see some weird reagents, once you have it memorized, you'll say, oh, this is probably that weird section. And now I have some tools to get myself through this. Okay. So maybe I'm sounding a little paranoid because just because of my experience as a college student, I was sick. I was out for a week, I think with strep throat. I can't remember exactly what it was, but I remember coming back to class and everyone was already working on homework and stuff. I was like, what's going on? Anyways, hopefully that's not your experience. You do have this video you can go fall back on and rewatch to get through this material. So here we go. Why don't we do an overview, just kind of see where we're headed. Now, we're going to end Unit 3 by discussing 4 different mechanisms, 4 classes of reactions, and unfortunately, they're very similar to each other. I actually have another video where I'm going to just highlight the main differences between these 4 reactions, Sn2, Sn1, E2, and E1. So take a look at that. And then, like I said before, a section is not about one specific reagent. There's a huge number of possible reagents that could show up on your exam and can show up in the laboratory. And the other problem is that you pick some reagents, you pick some solvents, pick an alkyl halide, and you're expecting one product. And sadly, technically, all 4 of these potentially could occur. And what we want to do is avoid that. We want to set up conditions, maybe choose a solvent, choose an alkyl halide, choose a reagent, the nucleophile, such that we get predominantly one of these 4 coming out. Okay, so how's that going to work? Well, as we choose reagents, solvents, alkyl halide, and so forth, the task is to set up one of these 4 to run the fastest. That's the key. The fastest reaction is going to determine the major products. Okay, so the bulk of this video is about the factors that influence the rate of reaction. So as long as we remember there's going to be 4 of them, 4 reaction mechanisms, but there's also 4 factors. Now, if we remember those 4 factors and what speeds or slows down each of those factors, that'll be extremely useful to us in getting through this section. Okay, let's get into it. We're going to start with the Sn2 reaction. And why don't we just, and again, memorize the mechanism, not necessarily the reagent. So here's an example of an Sn2. Well, if we take butane, 4 carbons, and on carbon number 2, we're going to attach a halide. My favorite halide is bromine, but it could be any of the halides, not fluorine. Remember, fluorine is found in Teflon, nothing sticks to Teflon. Yeah, fluorine's the kind of the exception of the halides. So chlorine, bromine, or iodide. And then let's reintroduce a little chirality. Let's make this second carbon of butane a chirality center and have the bromine facing towards us. That's a wedge bond. Bromine's coming out of the screen. Okay, and then I'm gonna pick some random reagents, ones you've never seen before. There's that thing. And then here's an abbreviation, an acronym. DMSO is a solvent. It stands for dimethyl sulfoxide. Sorry, a little hesitation there. Dimethyl sulfoxide. It has this structure. We'll see it again at the end of this video. It's something you do want to memorize. It's very useful for Sn2 reactions. Okay. First thing to realize is that DMSO is a solvent. It's not a reagent. So don't put any atoms in the products that are in the solvent. The solvent is just dissolving everything, helping the reaction go. Instead, you have to break down this weird NaSH. What the heck is NaSH? That's sodium with sulfur and hydrogen. And you get a periodic table on all my exams. So where's sulfur? It's right here below oxygen. It's in the same family as oxygen. Remember, elements in the same column belong to a family. Why are they family? Why are they similar? Because they share similar properties. Mainly because they have the same number of valence electrons. Electrons on the surface of the atom. Yeah, so the surfaces of all these atoms look the same, and they behave very similar to each other. Nice trend to remember, because what the heck is sulfur going to do? Probably something that oxygen does. Okay, so that's our first clue. Where's the pen? There it is that if we know the reaction with sodium hydroxide, we can predict the reaction with this molecule. Okay, so what is the product? Well, it's an Sn2 reaction, and how you figure that out, we'll get to later in this video. Sn2, well, S stands for substitution. So what we're going to do is take away the bromine and put on another group. The N stands for nucleophile, and that's the group that's going to be substituting. So let's look at sodium hydroxide. Which atom, Na, O, or H, is the actual nucleophile? Okay, so think about what the heck was a nucleophile? There also was an electrophile. We'll break down the name. Nucleophile, the phile part means loving or seeking. And so it's a molecule or a compound or an ion, something that's seeking the nucleus, and the nucleus is positive. So which atom here is seeking a positive charge? Well, the negative oxygen. So not the sodium, that's actually a spectator ion. Na is just helping make this compound stable. Same thing here in the actual reagent, NaSH, the sulfur is actually negative. The sulfur, like oxygen, prefers 2 bonds. Same family, same pattern. Oxygen likes 2 bonds. So currently sulfur is making a covalent bond to hydrogen, ionic bond to the metal sodium. And afterwards, sulfur is going to keep its hydrogen, 1 bond, and make a new bond to this carbon. Right? Substitute, pull off the bromine, add in the SH group. No sodium, sorry, see you later, sodium. It's actually going to hang out with the bromine. And I put it in parentheses because you don't have to write that part on the exam, because there's no carbon. Organic chemistry is a study of carbon. So organic chemist says, that's just waste product. I'm not even going to write it down. One other feature, though, is that the stereochemistry changes or it inverts. The group bromine used to point towards us. Afterwards, after substitution, the nucleophile, that group is actually pointing away. Okay, that's kind of crazy. We'll explain why in just a second. Did I finish explaining Sn2? No, I got to the S in the end, and then I diverted and wrote the products up here. 2 stands for bimolecular, second order kinetics. Why are we talking about kinetics? Because right here, the fastest reaction is going to determine the major products. So knowing second order kinetics helps us predict that in certain situations, Sn2 could win the race and be the fastest and predict the products. Determine the products, I should say. Okay, enough about the overall reaction. Let's get into this inversion of stereochemistry, it's called, where if you have the halide, oh, right, I should write that down. These Sn2 reactions primarily work with alkyl halides, right? An alkane with the halide, the alkyl halide functional group. And the halide is going to be substituted out with the nucleophile. And for Sn2, the stereochemistry inverts. So if, and that's the if, this doesn't have to be a chiral center, but if it is, and you only have 1 enantiomer, like we do here, we don't have the bromine on a dash bond. We don't have that compound, the other enantiomer. We only have the one with the bromine facing us on a wedge. Then it inverts. You have to realize that as you predict the products and change the wedge to a dash. You have to invert it. Okay, let's look a little history where this came about or how we discovered it as scientists discovered it. Well, Walden here did this series of reactions. You don't have to memorize this. It's just kind of interesting, and it's a way that gives you an insight as to how chemists do science and figure out these reaction mechanisms. Okay, back in the 1800s, I believe, he took this molecule that you can isolate from apples. In fact, malic is derived from the Latin word for apple. I had to look that up. And that's where the common name comes from for this molecule. Anyways, is there a chirality center somewhere in this molecule? Let's try and find a carbon with 4 different groups, and it's right here. This carbon has a hydrogen, an alcohol, a carboxylic acid group, and over here is a carbon, then the carboxylic acid group. There's 4 different groups. And it turns out nature oftentimes prefers to make one enantiomer. When she could make both, she doesn't. She's like, I'm just going to make the one. So it turns out, yeah, the levorotatory, you put this in the polarimeter, rotates light counterclockwise, and here's the angle of rotation. Cool. So take this pure compound, one enantiomer from apples. Walden treated with PCl5 in the solvent ether and did a substitution reaction. Cool. It's still a chirality. It's still a chiral molecule because it rotates, the product rotates light positive. And yeah, don't worry about the actual sign changes here. We'll move on. Chlorine then gets substituted back to an alcohol using silver oxide in water as a solvent. What did he do? He just remade the exact same molecule. Or did he? Wait, the chirality changed. It was inverted. It used to be a levorotatory, now it's a dextrorotatory. Now it rotates light exactly opposite. This is the pure enantiomer. And so what Walden discovered is, it looks like he's not doing anything here. He starts with malic acid, ends with malic acid, but the series of 2 reactions inverted the stereochemistry. He proved it, put it in the polarimeter. And then to ultimately prove it, he can switch it all the way back. He used a PCl5 to switch the alcohol back to a chlorine, silver oxide, take the chlorine back to the alcohol, and finally, in 4 reactions, got the original molecule back again. That's called the Walden cycle because it cyclizes there. But it proves that you're inverting the stereochemistry either at this step or this one, and I think it is this one where the sign changes. Not always true, but anyways, interesting data. If anyone asks you about the Walden cycle, hopefully that'll ring a bell. It's referring to this series of reactions that are investigating Sn2 reactions, specifically inversion of stereochemistry. So Walden proposed this idea that, let's just get to this point. It's like an umbrella turning inside out in the wind. Maybe you've had that happen to you. If you think about an alkyl halide, and we actually have one, right? So let's take a look at my example I wrote up here, where you take this 2-bromobutane and treat it with NaSH. Get that little picture down here. That works. Okay, we'll draw it up here. We'll draw that 2-bromobutane in a similar fashion here. So this is carbon 2. And then let's put carbon 1 of butane on a wedge bond. And we'll put the hydrogen on a dash. And then in the plane, oh, kind of messed it up. It's not exactly the same. It doesn't matter. Here's the rest of the 4 carbons. Cool. And then let's bring in the SH. That's our nucleophile. And then I'm not going to draw the transition state, but there it is. It's the halfway point where this bond is half made and this bond's half broken. the leaving group. That's why it's an L, which is a halide. That's going to leave, be substituted out. Nucleophile comes in. And the idea is that the lone pair on the sulfur, the nucleophile, is going to attack this carbon. Well, why? Well, you got some partial charges here. Who's more electronegative, bromine or carbon? I'll go to the periodic table and take a look. Where did I hide that periodic table? It's over here on the right. Bromine or carbon. So quick little review of electronegativity, right? Fluorine is the bully. It's the most electronegative. Bromine is 2 steps away, but carbon's 3 steps away. And the trend is the farther from fluorine an element is on the periodic table, the less electronegative it is. Okay, so bromine is more electronegative. It's hogging up the electrons, pulling on the electrons more than carbon pulls back, creating a polar covalent bond. Bromine slightly negative, carbon slightly positive, and that polar covalent bond is what draws in the nucleophile. That's its nature, nucleophile seeking a positive charge. And so the lone pair on the sulfur is going to make a new bond to the carbon. The carbon can't make 5 bonds. So at the same time, the bromine leaves, and it's been doing the tug of war on these electrons anyway. So it finally wins the tug of war and leaves with a lone pair. And so you get the nucleophile, which is sulfur, adding to carbon. As it adds, though, right, the carbon is sp3 hybridized. It's got 4 bonds. The bond angles need to be 109.5. So if the sulfur came in from the left side, all of these groups have to swing over to the other side, just like an umbrella, you know, the folds actually invert, swing over to the other side. So none of these bonds get broken, they just get moved. So the hydrogen stays on the wedge, but it flips over from pointing slightly to the left to pointing slightly to the right. Same with the methyl. And the alkyl group swings over too. And it turns out if you rewrite this such that, how do we have it before? Like this, stretch out the chain, then the bromine would end up on a wedge, sulfur ends up on a dash, as the stereochemistry is inverted. Cool. Okay, that's the mechanism, by the way. Should have pointed that out. That's kind of important. Mechanism. I like Sn2. 1 step, 2 arrows. There are a couple exceptions to that, but for the most part, 2 arrows, 1 step. So much better than initiation, propagation, termination, right? That's a long mechanism. Let's see, what else do we need to know? The 2 again. The 2 stands for second order connects, right? Sn2. Okay, so here is the rate law for the Sn2 reaction. The rate is equal to K, the rate constant, times the concentration of the alkyl halide times the concentration of the nucleophile. So there's 2 molecules involved in the rate determining step. There's a little general chemistry again. But if you don't remember that, just remember this equation. The speed of the reaction is going to determine the winner between these 4 mechanisms, Sn2, Sn1, E2, and E1. And we want, in this case, Sn2 to win. So to help it win, increase your concentration of alkyl halide. As this increases, the rate will go up too. Also increase the concentration of the nucleophile. As the concentration of the nucleophile increases, so does the rate. And you should know that, you know, if you double one of those concentrations, that will double the rate. Quadruple the rate if both of these are doubled, right? Okay, you should know that pattern. So then, here we go to the main idea of this video. There are 4 factors that influence the rate of all these mechanisms, and they involve the alkyl halide. Primarily, this is the structure of the alkyl group, and we're going to look at whether the alkyl halide is secondary, sorry, I should say in the order, tertiary, secondary, or primary. The nucleophile, the thing with the lone pair, what's the structure of that, its properties that can influence the speed of how it works. And then the leaving group, well, we could choose chlorine, we could choose bromine, we could choose iodide. There's another one coming, another leaving group, and that affects the rate of the reaction too. Which halide you use will speed or slow down the reaction. And finally, there's a solvent involved. And then the solvent can either help speed up one of these reactions, or it can interfere and slow down one of those reactions. And knowing how these four factors influence the reaction rate will help us decide which of these four mechanisms will dominate, go the fastest, and actually produce the products, the major products. All right, that's what we're going to do for the rest of the video. Let's look at these four factors in turn, beginning with the effect of the alkyl halide. Top of the next page. Okay, so we're going to look at some data to try and ascertain what the pattern is, right? It's all about patterns. So what we got here, we're looking at the alkyl halide. Here is the overall reaction. R just means some set of carbons with the halide on it. And here's our nucleophile. I'll abbreviate nuc. It's chlorine ion. Well, the chlorine ion has 4 lone pairs. And to be a nucleophile, you just need 1 lone pair. And then what's the identity of the R group? Well, if it's tertiary, here it's the structure. Something called neopentyl. It's a common name. Don't worry about that so much. Just look at the structure. So this halide over here on the far left, what degree is this halide? Is it primary, secondary, or tertiary? Well, it says tertiary here. But you would ask a carbon, hey carbon, what degree are you? And this carbon say, oh, I'm attached to 1, 2, 3 carbons. I am tertiary, so the bromine's also tertiary. How about this bromine? Talk to this carbon, and this carbon says, I'm primary. Okay, this bromine, talk to this carbon, it's attached to 2 carbons, making it secondary. Well, that's what it says down here. What about this halide, this bromine rather, it's primary. And then we even have the methyl one. Is that like a 0 degree? I don't know, it's just methyl. All right, what are these numbers down here? That's the relative reactivity. That's a measure of the rate of reaction. So if you take tert-butyl bromide, and that's what this group is, and add some chlorine ions, so maybe some table salt, NaCl would have the chlorine ions. Let the reaction go a while, it's really slow. The other reactions are fast. It's less than a rate of 1 molecule per minute. I don't know what the units are. This crazy molecule is primary, but it's not going very fast, a relative rate of 1. The secondary halide is going 500 times faster than this one. The primary is going 40,000 times faster than this one. And the methyl is going the fastest, 2 million times faster than this one. Okay, so what's the trend? The more alkyl groups, the slower the reaction. It's all about crowding here. And the sciencey word for that is steric hindrance. There's more steric hindrance as you put more bulky groups on the carbon attached to the halide. Okay, so that's our pattern. Sn2 does not like crowding. Less crowding, faster reaction. Boom, we're done. Okay, so then students remember, oh yeah, so for Sn2, I'll just memorize methyl's the best. That goes the fastest. If you have a methyl halide, it's probably going to be Sn2. And then if you have a primary alkyl halide, it's probably Sn2. Secondary, it might be. But if it's tertiary, that's supposed to be a degree symbol, not 30. I'm going to put that in parentheses. Sn2 is going to be too slow. Someone else is going to be faster. Sn1, E1, or E2. So tertiary doesn't work well for Sn2. Someone else, some other mechanism is going to win and determine the products. You got to be a little careful here. This is true. Methyl generally is faster in primary, faster in secondary, but this one's primary. So you really have to look at the structure and say, okay, look at this crazy tert-butyl group right next to the primary carbon. So that's going to slow it down. Okay, so it's really best to know less crowding, and don't just rely on the degree to determine the outcome. Okay, that's our first factor, the alkyl group. How crowded is it? We don't want much crowding for the Sn2 reaction. Next factor, the nature of the nucleophile. So I got words all over the place, sorry, just kind of ignore some of those. Let's just look at the data. So here's a new set of data. We're going to pick one of the fastest alkyl groups to work, the methyl one. So we want a fast Sn2 reaction. And now we'll change the nature of the nucleophile. So which group has a lone pair? Lots of things. This time it's an oxygen, or the oxygen of water, oxygen of acetate. Well, let's use the lone pair on nitrogen of ammonia. Oh, put in chlorine again, that is a lone pair. How about the lone pair on hydroxide? Or let's substitute out the hydrogen, put an alkyl group. Iodine's a different halide, lone pair, cyanide ion. There's the Lewis dot structure of cyanide. There's two lone pairs. Turns out carbon is the more reactive one because carbon wants 4 bonds. Nitrogen's happy with 3 bonds. That lone pair is not very reactive because nitrogen's like, he's good. Carbon's like, I'm not good. I want 4 bonds. So this lone pair on the carbon is the reactive part of the nucleophile. And then hydrosulfide, we saw NASH, right? NaSH, there it is. Just like oxygen is a lone pair, sulfur, oxygen in. Anyway, same family is what I'm trying to say. Sulfur and oxygen, same family. They're going to behave similarly. Change the nature of the lone pair and look at the rates change here. Kind of crazy. And I just kind of like, whoa, is this something we have to memorize? The answer is no. We want to find trends though. So we got a couple trends listed in our key concepts. Let's move this over here. Is that going to be a good spot? Let's slide over here a little bit so we can see these trends. Am I losing my data? A little bit. Good enough. Okay. First trend, I'm looking over here. More basic, better nucleophile. Okay, more basic, better nucleophile. What are we talking about? Well, let's just pick out a couple of these nucleophiles. Let's compare water with hydroxide. Who's more basic, right? Water is a weak acid and a weak base. Hydroxide ion is a strong base. Okay, so there's a lone pair on oxygen, lone pair on oxygen. We're comparing apples to apples. But here, hydroxide is more basic than water. So it's going to be a better nucleophile. Yeah, it's 10,000 times faster. Hydroxide ion does the Sn2 reaction 10,000 times faster than water. Water is not a very good nucleophile for Sn2. Okay, that's the first trend. What else we got? Going down the periodic table, elements become more polarizable and better nucleophiles. Okay, so polarizable is just a way of trying to explain why they're becoming better nucleophiles. Polarizable, you kind of think of it like a sponge versus a rock, right? So a sponge is kind of squishy. It can change or deform its shape. Rock, not so much. So if you start at the top with chlorine, actually, you can use fluorine as a nucleophile. Chlorine is a small and hard rock, doesn't change its shape very much because there's only what? There's only 2 shells. It's in the second row. Let's look at this. This will help, right? So there's 9 electrons in an atom of fluorine, only the 1s and the 2s and the 2p electrons here. Pretty small hard rock in terms of number of electrons around it. It's not very malleable, very deformable. Chlorine, though, has 3 shells. Bromine has 4. Iodine has 5. And now it's getting kind of squishy. So oftentimes we think of an atom, or in this case, ion, as nice and spherical, nice, perfect sphere, roundish. But that's not true. These electrons are in motion. So with 5 shells of electrons, sometimes you get more of an oval shape. And what if, let's see, we got 53 electrons, but when it's I minus, there's 54. What's half of 54? 27. So we got 54 electrons in I minus. On average, 27 electrons should be on the left side. The other 27 electrons should be on the right. But what if for an instant there's 28 on this side of the line and there's only 26 over here? Well, then this side is slightly negative and this side is slightly positive. If you have a fluorine, well, there's 10 electrons there. So typically that's like 5 and 5, and you might get 4 and 6, but it's such a small thing. It's probably going to stay pretty close to 5 and 5. It's not very polarizable. You're not going to have one side that's slightly more negative, another side slightly positive. But as you go down the periodic table, they become more deformable, more polarizable. And if they're polarizable, does that make for a better nucleophile? Well, let's compare iodide versus chloride. Chloride in the Sn2 reaction goes about 1,000 times faster than water. Iodide is 100,000 times faster. So the difference between these two is a factor of 100. Iodide is 100 times better as a nucleophile than chloride. Yeah, that's a good trend to know. If you want the Sn2 reaction to go and you don't care about what is substituting, you don't care if it's chlorine or iodide, you need to pick, go with iodide. That makes for a faster Sn2 reaction, and it should be the winner, not E2, E1, or Sn1. And then for me, personally, those are the only two trends you really need to know. Compare the nucleophiles, decide who's the stronger base. All right, let's do that. How about this molecule versus ammonia? Well, you may not have ever seen this molecule, but it looks like hydroxide with a negative oxygen. From gem chemistry, you should know, hopefully you remember, ammonia is a weak base, but hydroxide is a strong base. And it turns out if you put a carbon instead of a hydrogen on there, it actually makes it slightly more basic. I'll explain that later in another video. So this is a strong base, this is a weak base. And that's what trend 1 says, the more basic, the faster or the better the nucleophile. Yeah, 700 times faster than water for ammonia, but the methoxide ion, that's the name of that thing, is 25,000 times. So this number is bigger than that number. This is a better nucleophile. The other trends you go down, right? So iodide is faster, better nucleophile than chlorine, but so is sulfur compared to oxygen. So sulfur, HS minus compared to HO minus, yeah, the sulfur ion is faster than the oxygen ion. 10,000 compared to 125,000. Cool. So remember those two trends. There is a third one. I got it written down here. Gotta reorganize this a little bit. There we go. Trend 3 says anions are more nucleophilic than neutral compounds. For me, it's like, wait, you're just repeating trend number 1. But it's true. If you, I don't have it up here, but if you had nitrogen, the nitrogen anion compared to ammonia, you'd say, oh yeah, negative nitrogen's a better base than the weak base NH3. So you would already use trend 1 saying, this is more basic, it should be a better nucleophile. The trend 3 is saying, hey, but this is negative and this is neutral, so that fact alone should be a better nucleophile. For me, it's the same thing. Being negative makes it a better base. That's trend 1. Okay, let's get down the nitty gritty. Do we have to memorize all these different nucleophiles and how efficient they are? No, just remember the trends. More basic, better nucleophile. Moving down the periodic table, better nucleophile. I don't recommend memorizing these. On the other hand, it is kind of handy. I have some students say, well, if I memorize them, then I'll know when I see them that they're probably Sn2. Remember that little probably. Doesn't guarantee. There's 4 factors. Nucleophile is just 1 factor. So yeah, I have a list of nucleophiles. I'll show it right here. So I stole it from this website, so I'll give them credit. And it's kind of cool the way they categorize them. So they looked at the different molecules with lone pairs. They can act as a nucleophile for Sn2 and Sn1. They can also work as bases for E1 and E2. So this is categorizing them and helping you figure out which nucleophile acts like a nucleophile and which time does the nucleophile act more like a base. We'll look at that again later. So if you like that list and you want to commit the memory, I'm not advocating that or recommending that, but it's there. Here's a better idea. I had another student say, just remember, good nucleophiles are strong bases and Sn2. And the S stands for sulfur, the N stands for nitrogen. And I thought, that's so clever. So if you go to the trend up here, things are basic, are better nucleophiles. So good nucleophiles are strong bases, hydroxide ion, methoxide, yeah. And Sn2. So the nucleophiles with an S, nucleophiles with an N, they tend to be good nucleophiles as well. I like that. Good nucleophiles are strong bases and Sn2, sulfur and nitrogen too. Okay. Oh, functional groups are good to know too. So sulfur functional groups are thiols. Nitrogen shows up in amines. So thiols and amines tend to be good nucleophiles for Sn2. That's the second factor. We had the first factor was primary, secondary, tertiary alkyl halides, less crowding, better for Sn2. And for the nucleophiles, we got good nucleophiles are strong bases and sulfur and nitrogen too. Third factor, the leaving group, the nature of the alkyl halide, the halide group. So what's the pattern? Well, iodide's the best, fluoride is the worst. So there's, in fact, this chart actually includes other potential leaving groups. So if you had an alcohol group and you said, hey buddy, can you do an Sn2 reaction? The hydroxide group says, nope, I don't go very well at all. What I remember though is Sn2 reaction and the Sn1 and the E1, E2, they primarily react with alkyl halides, and this is not an alkyl halide. So that's how I would just say, hey, hydroxide, you're not going to react here. The alcohol group, rather, you're not going to react here. This molecule is not an alkyl halide. So therefore, no reaction. Or at least no Sn2 reaction. Chloride works really well, but bromine is better. Iodide is even better. And what the heck is TOS-O? TOS-O stands for tosylate. It's another leaving group, and it's the best. So guess what? We have another reaction to learn. Remember, we just said the alcohol group doesn't do Sn2 reactions. But a little loophole is you can change the alcohol group into the tosylate group. We pull off this H, and we put this whole thing on it. And then with the oxygen, that group is called a tosylate. Where's that crazy word tosylate coming from? Well, benzene rings with a methyl group has a common name called toluene. So there's a TO, and this sulfur is like a sulfoxide group. That's the S. Anyways, that's where it's coming from. So I need you don't have to remember the solvent, but you do need to know how to make tosylates out of alcohols, because they can do the Sn2 reaction the fastest. Sadly, this trend is the same for everybody. E1, E2, Sn1, Sn2. So it turns out changing the leaving group won't help determine a winner. Changing the leaving group just makes everybody faster. So it's a good information to know. Like if in the lab, you're like, I really want this Sn2 reaction to happen now and today, well, then you should probably go make the tosylate or get the iodide, alkyl iodide, And the chloride ion, you're gonna have to let it store overnight maybe, or you have to wait a while. It won't go as fast. Let's see, more details. You can write tosylate here, so in your functional group. So I'm just rewriting this portion of the molecule. And you could write OTS, you could call it OTOS. However, when you're given the reagents, you really need to draw it out. So you have to memorize that group. So here, take a primary alcohol. Why primary? Because we're trying to do Sn2. It's a less crowding, faster reaction. Sn2 still works on secondary. So you can use secondary. You don't want to use tertiary. Not for Sn2. But maybe you're going to use one of the other mechanisms, and tertiary works. You can make tosylates out of them, but the tertiary tosylate, tertiary halide doesn't do a very fast Sn2. Someone else is going to win. Okay, I'm easily distracted, sorry. So this molecule is called tosylchloride. There's a methyl group where you just form a line. And then you have to use pyridine. You may abbreviate it PYR. That's fine. Or you can draw it. It's benzene with a nitrogen as one carbon. And you can draw it however you like. Remember, when you're drawing it, you decide how you want to draw it. These two are both pyridine. There you go. And then wherever the alcohol is, you substitute the hydrogen with the sulfur and the rest of the atoms. You make HCl, those two combine, they leave together, and that's an acid. Pyridine's a weak base. Pyridine serves as an acid scavenger, it's called. It's neutralizing the acid. If you have too much acid building up, you can get a side reaction with the tosylate. So that's the role of the pyridine, is to quench the acid that's produced. But here we go. I'll draw my benzene ring that way. That is a tosylate. Okay, so you need to know these reagents because it makes for a good leaving group, and you can do these Sn1, Sn2, E1, and E2 reactions much more quickly if you have a tosylate instead of a halide. Did I miss any other key points? Yeah, this is an excellent way. Tosylate's an excellent way to change an alcohol into alkyl halide, right? So the alcohols don't do these reactions, but you modify them by changing them to a tosylate group, they will. The other ideas we saw in a previous video, you can change alcohols into alkyl halides with thionyl chloride, SOCl2, and phosphorus tribromide, PBr3. And that works, but tosylates work faster, so that might be your preference. And then you might say, hey, the rate up here, iodide's going 30,000 times faster than fluorine, tosylate's 60,000 times faster, so there's only a factor of 2. Tosylate's just twice as fast. Is that really worth all the extra work? There's one more advantage tosylates give you, is that they have good shelf lives, meaning you can make tosylate, put it in the, put it on the shelf in the stock room. It's pretty stable. Alkyl iodides, though, they slowly decompose. So you'll see more tosylates in Sn2 reactions than you will iodides. Oh, there's no mechanism required on the exam for making a tosylate. If you want to see it, I can show it to you. Not on the exam, though. There we go. Main trend is leaving groups that are more stable anions are faster give a faster reaction. So the iodide, right, as you go down the periodic table, F- is actually a weak base. Chloride's not basic. Bromine's even more stable as an anion, iodide even more so. And we know that because HCl is a strong acid, but HBr is a stronger acid. And HI is even stronger than that. Iodide is very willing to give up H+ and exists as I-. It's a very stable anion. Fluoride, though, no. Fluoride's like, I don't want to release H+ so much because once I'm F minus, I might want to grab it back. It's a weak acid. Fluoride ions are somewhat basic, weak bases. That makes them terrible leaving groups. Like they don't want to leave. They don't want to break the bond. And again, sort of like Teflon. That's how I remember it. Fluoride's not a good leaving group. Doesn't do Sn2 reactions or any of the other reactions, E1, E2, or Sn1. All right, leaving group was our third factor. Fourth factor is a solvent. Last one. So let's move this here. Can I make this bigger? That's going to be too big. Sorry, font's pretty small. Sorry about that. Okay, let's look at the solvent. We're going to look at one specific reaction. We're going to take one bromobutane, cool, and then this crazy molecule, that's called azide or azide, a couple different ways to pronounce it. 3 nitrogens, net negative charge. One of these nitrogens has a lone pair that's going to bump out, replace the bromine. Invert the stereochemistry like the umbrella, and you get this product, right? So we've never seen this reagent before, but we could recognize the pattern. We have an alkyl halide that's primary. Primary alkyl halides are fast for Sn2, there's less crowding. And then this group is negative, anions work faster than neutral compounds. Okay, so substitute them out, there's your product. Okay, so repeat this exact same reaction in various solvents. We can use methanol, CH3OH, we can use water. Hey, water's 7 times faster. DMSO, we saw earlier, it's right here. There's the structure again. It's 1,300 times faster. That's a better solvent for Sn2. If you use water or methanol, turns out another reaction is going to be faster than Sn2. So don't use these for Sn2 reactions. If that's your objective, you want the Sn2 to work, don't pick these solvents. Sn2 gets slowed down by them, allowing another reaction to go faster and win and determine the products. Don't have to use DMSO, you use DMF, dimethylformamide. The amide group, hence the name here. So you remember amide is a nitrogen next door to a carbon-oxygen double bond. Form, that comes from a Latin word probably for one. I don't know where it comes from. Anyways, but form talks about this carbon is the only carbon of the amide group. There's not a methyl group here, in other words. On the nitrogen are 2 methyls though, dimethylformamide. We'll just abbreviate DMF. Acetone has a similar structure to DMSO, dimethyl sulfoxide. Just change the sulfur to a carbon, and that's acetone. Ladies, you know acetone is nail polish remover. That's a great solvent. Yeah, it's also a great solvent, not only for your removing nail polish. It's not listed up here. It's also a good solvent for Sn2 reactions. Acetonitrile, ethane nitrile is the IUPAC name, where you have a methyl group on the cyanide ion, but it's not, it's a covalent bond. That's acetonitrile. That works really well, 5,000 times faster than methanol. This crazy solvent is toxic, so we're not going to use it. So I know the data is here, HMPA, hexamethylphosphoric triamide. No, we're not going to use that. It's expensive too. More importantly, it's toxic. One comment about DMSO, it's a really good solvent. You gotta be a little careful if you use it in the lab because it's readily absorbed in the skin, by the skin. In fact, they actually use this in some animal medications. So talk to your vet, see if they ever use DMSO. DMSO itself is not toxic, but the toxicity comes about because it dissolves a lot of stuff. So if you spill DMSO on something where you spilled some chemicals that are toxic, well, the chemicals will dissolve in DMSO. You put your hand in it, DMSO will penetrate the skin and carry along the molecules that are dissolved in DMSO. And then you get poisoned by the stuff that's dissolved in DMSO. Works great on, I understand, like horses. You can put some antibiotic, dissolve in DMSO, put it on a wound of a horse, and the DMSO will kind of dissolve into the wound and carry in the antibiotics. to help stop an infection. Cool. So be careful with that if you use that in lab. Actually, be careful with any of these. Not intrinsically toxic, but if they're contaminated, yeah, think you're rolling the poison. Okay, back to Sn2. You want to use these solvents, not water, not methanol. What's the pattern? The bad solvents for Sn2 are ones that can hydrogen bond. They can H bond, so don't use them. Turns out Sn1 prefers those. That's a topic of our next lecture, next video. Sn2 though, let's choose solvents that do not hydrogen bond to each other. And remember, for hydrogen bonding, you need an HF, an HO, or an HN bond. So that's why this nitrogen has two methyls, not a hydrogen, because then it could hydrogen bond. Water is a great hydrogen bonding example because there's two OH bonds. Carboxylic acids can hydrogen bond. So sometimes we use vinegar, acetic acid as a solvent in our lab. You don't want to use that for Sn2 because vinegar has acetic acid in it, also has water in it. They both hydrogen bond and they slow down the Sn2 reaction. How do they do that? If you like reasons, it's because they form a solvent cage around the nucleophile. So the nucleophile is going to have a lone pair, and that's what you need to make a hydrogen bond, right? So water hydrogen bonds this way, right? A lone pair on one water molecule will make a weak, not a covalent bond, but a weak hydrogen bond to the hydrogen of an adjacent water molecule. And if that's your nucleophile with a lone pair, the solvents that can hydrogen bond will actually make hydrogen bonds to your nucleophile and bind it up, put it in a solvent cage, and keep it from reacting with your alkyl halide. It slows down the reaction. So don't use a hydrogen bonding solvent. Hydrogen bonding solvent, I can't even say it easily. So there's another word for it. So if you don't have an H for hydrogen bonding, hydrogen has a proton in it, one and only proton, its nucleus. So the name of these solvents that can hydrogen bond, the ones with a hydrogen, a proton, they're called protic solvents. And if you don't hydrogen bond, it's called aprotic. So you'll need to know that. The technical term is that we want to use a polar aprotic solvent for Sn2. Why does it have to be polar? Because we're using nucleophiles with lone pairs. That's going to be slightly negative. We might even be using anions as our nucleophile. They're definitely going to be polar. So you can't use a non-polar solvent. So like hexane, that's a component of gasoline. It's a solvent, but it's a non-polar solvent, and it's not going to dissolve table salt, right? We use chloride ions in a previous Sn2 reaction. Table salt's not going to dissolve in gasoline. NaCl is not going to dissolve in hexane. That's if you can't dissolve the nucleophile, you can't get it to collide with your alkyl halide. So you need your solvent to be polar to dissolve the nucleophile. And it can't be just any polar solvent because water doesn't work. The alcohol groups don't work. Carboxylic acid groups don't work in your solvent. No, you have to have solvents that don't hydrogen bond, and the term for that is aprotic. Cool. So last things here. Okay, so bottom line is you do have to do a little memorization. You should know the structures and the abbreviations for these four. They're great for Sn2 reactions. These will be the Sn2 solvents. So if you see these show up underneath the reaction arrow, right? So at the beginning of this video, we had NaSH with DMSO. That's one of the Sn2 solvents. It does not guarantee Sn2. It's trying to help the Sn2 reaction go. You then have to look at all four factors to decide, okay, is Sn2 going to win the race against Sn1, E1, and E2? Look at the alkyl halide. Is it primary or secondary, or maybe methyl? Less crowding, faster Sn2. Look at the nucleophile. On this case, sulfur, nucleophiles are good. Nucleophiles are strong bases, and Sn2. Hey, there's the sulfur. in my nucleophile, that's probably a good nucleophile for Sn2. Look at the leaving group. Are we using iodide or tosylate? That's going to make for a faster reaction. And then the solvents or force factor. DMSO, that's one of the solvents that's useful for Sn2. And if Sn2 wins a race, then you predict the Sn2 products using the Sn2 mechanism. Oh boy, what else I got? I think that's it. I meant to cut and paste one more thing. Let me go get it. I'll just end on this note. Can you see that at all? Little meme. I like it. Yay. Finishing up with polar solvents. Poor polar bear. All right, that's enough for now. I'll see you in the next video.